Hi, in this video we're going to be talking about infinite series. So suppose we have a sequence, and the members of the sequence are indexed by I, and they're called a sub i's. And from this, we can define S1 to be A1, S2 to be S1 plus A2, or A1 plus A2, S3 will be A1 plus A2 plus A3, or S2 plus A3, and so on, where our nth position is going to be A1 plus A2 all the way up to AN. Now each of these SNs are called partial sums of the sequence. And these partial sums themselves actually form a sequence themselves. So a natural question to ask is, what is the limit of this sequence? Well, the limit as n approaches infinity of Sn is going to be A1 plus A2 plus so on and so forth to AN and continuing. We can rewrite this as the limit as n approaches infinity of the sum as I goes from 1, which is just our starting index, to n of a sub I. And we can shorten our notation. Instead of writing the limit as n approaches infinity, we can just write 1 to infinity of a sub I. The important thing to note here, though, is that we are still taking a limit. So we're still taking a limit, even though our notation doesn't explicitly say so anymore. So the limit of our partial sums, or the sum from 1 to infinity of a sub n, is called an infinite series. Now, we're going to talk more about convergence and divergence, but let's make a couple of notes before we get really deep into it in the next couple of videos. So the first thing is that if the limit of our partial sums converges, then our sum itself converges as I ranges from 1 to infinity. And if the limit of our partial sums diverges, then so does the sum itself. So does the sum as I ranges from 1 to infinity of AI. Now, an additional note that we're not necessarily going to write down is that this I equals 1 and this I. Note that even though we have i's over here, we used n further up, and in the future we're going to use k's and j's and a bunch of different variables. These are what's called dummy variables. So, dummy variables. So, what a dummy variable is it's just a placeholder for a variable. And it does, just like how if we were to integrate x squared from 0 to 1, and we were to integrate y squared from 0 to 1, it wouldn't really change anything at all. It's just which variable we're using. So now, let's look at some properties of infinite series. Now, since we're just adding stuff up, we have properties that are very similar to just adding two things together. So if we were to take the sum of a sub I from 1 to infinity and add that to the sum of b sub I from 1 to infinity, this is the sum from 1 to infinity of a sub I plus b sub I. Now, an important note here is that they must start at the same place. So at the same index. So we can't have the sum from 2 to infinity of a sub I plus the sum from 0 to infinity of b sub j. That won't give us what we want. And in order to deal with that, we're going to talk about that in the next video, when we actually talk about index shifting and how to get these starting points the same. The second property that we have is constant multiplication. So if we have some c times ai as I ranges from some starting point to infinity, that's the same as ca1 plus ca2 plus and so on to can. And what we can do here, let's go ahead and move our multiplication property down before we talk about it, is we have a common factor of c, so we can pull that out. We get ca1 plus a2 all the way up to an, and the inside, we can have that c on the outside, and on the inside we just have the sum from 1 to infinity. We just keep going. We don't stop at an of a sub I. So all the constant multiplication property says is that we can take this constant here and pull it out in front of the sum. It's the same thing when we were talking about integration, where we can just pull a constant out of the integral. And the final property isn't really a property. This is like an anti-property. And what it says is that if I take the sum of a sub I, say from 1 to infinity, and I multiply that by the sum from 1 to infinity, that is not equal to the sum of a sub I times b sub I. And the way to see this is, what if we just take a partial sum? So we look at the sum from 1 to 2 of, let's say, I, and we multiply that by the sum from 1 to 2 of I squared. Okay, so if we were to actually look at it like this, we would have the sum from 1 to 2 is 3, and the sum from 1 to 2 of I squared is 1 squared plus 2 squared, so that's going to be 5 or 15. But then if we look at the sum from 1 to 2 of I times I squared, we're actually looking at the sum of I cubed from 1 to 2. And that is going to be 1 plus 8, which is 9. And these don't match up. So the simple example with partial sums in this case actually expands to the infinite case. Come join me next time for index management down here, where we'll be talking about how to get our indices the same starting point so that we can add things together. Be sure to leave a comment if you have any questions, comments, or concerns, and as always, thank you for watching.